So going on, so far we looked at TD estimates, right? TD evaluation of the policy. Now we would like to look at the control problem. So what is the control problem? The control problem is to learn optimal policies, right? And quite often, since we are actually learning from samples, right, we don't have the access to the full MDP. So at best, what we can guarantee is that we will get an approximate optimal policy, unless you have certain conditions on which on the samples that are being returned, right? That the sample is truly representative, and then you are visiting every state and every action in the MDP often enough through the samples, and then it will converge to the true optimal policy. But without that, we will have some kind of an approximation to the optimal policy. But the control problem is all about learning optimal policy. So how will we do this? Remember the generalized policy iteration idea, right? What a generalized policy iteration says? Okay, you take a policy pi, you do some kind of evaluation of policy pi, right? You don't have to, completely evaluate pi and get to q pi. You do some kind of an approximate evaluation of policy pi, get some estimate of q pi, and then you be greedy with respect to that. That gives you the improvement step, right? And again, only on the states that you evaluated the policy pi, you can do the improvement. Other states, it really doesn't matter because the value wouldn't have changed, right? And then you keep doing this, and as long as you are visiting all the states and actions often enough, right, and you will get the optimal value function, right? So for the policy evaluation step, instead of using what we did earlier, right, we did some kind of iterative policy evaluation and all that when we were looking at dynamic programming, right, when we talked about generalized policy iteration in that case, right. Here we will use just TD0. Right? So the TD0 will be used for evaluating the value function, and then the policy improvement is rather simple, right. We will just make the policy greedy with respect to the current value function, right. So you don't really even explicitly have to construct the policy. I can use the current value function for selecting what should be the next action. So as long as I am selecting like greedily or epsilon greedily from the current value function, right, I would be doing an improved policy over what was the previous version of the policy that I executed, right. So one thing to remember is that it makes sense for us to use action values than state values in this case. Why? If you are using state values, and if you are using state values, we will need to know the dynamics of the MDP to know which action to take, right. So I'll have multiple actions that I can behave in a given state. Which action should I take, right? I have to even pick greedily. I'll have to do a one-step look ahead, right? Remember how we did the optimal Bellman optimal value function, right? So we did a max over A, and then we had to look at what happens at the next state, right? Since we don't have access to the probability of transition and the rewards, we learn the action values where you can directly compare the q values of the different actions in the state, and I can take the action with the maximum q value, right? And or do this epsilon greedily or whatever, right? So that makes life a lot easier. Therefore, we learn the action value function rather than the state value function when we do TD control, right, and some form of generalized policy iteration, right? And so remember how we will set up this. So the policy will be set up, right, for we have to have some kind of exploration. So easy way to do it is epsilon greedy, but you can also set it up as a softmax exploration. So whatever fancy exploration technique you want, you can try here, right? But the easiest thing to do is to think of it as an epsilon greedy setup, right? So we'll stick with epsilon greedy for the time being. So I'll pick so A star, which is the greedy action according to the current estimate of the q function, right? And then the probability of me picking the greedy action, right? This is basically if pi A star of given S, right, is 1 minus epsilon, so which is the greedy action, plus epsilon by the number of actions. That's a small correction that you have, because with the probability epsilon, I pick any action. It's not that I pick a non-greedy action, I just pick any action. And of course, if it's not optimal action, I have some epsilon by the number of actions probability of picking it. So this is clear, right? This is something that we know already. So one thing I'm just going to state now without proof or anything is that if I'm always going to pick an epsilon greedy policy, right, with respect to the current value function q, right, then I will be guaranteed an improvement in the space of all epsilon soft policies. So what I mean by epsilon soft policies, it means that every action in the MDP in every state has at least epsilon by number of actions probability of being picked. So that's an epsilon soft policy, right? So for example, a uniformly random policy will be epsilon soft, right? As long as epsilon is a small, is a reasonable number, right? Uniform, random policy, which means all the actions are given same probability, will be an epsilon soft policy. And likewise, an epsilon greedy policy with respect to the value function will also be epsilon soft, because every action by definition has at least a probability of epsilon by n of being picked, right? And all the remaining probability is given to the greedy action. So that's basically what we mean by epsilon soft policies. And our policy improvement, we talked about policy improvement theorem, right? So we go from pi 1 to pi 2 to pi 3 all the way to pi star, right? The policy improvement theorem, which says that, okay, if you go from pi 1 to pi 2, and if pi 2 is different from pi 1, then pi 2 will be better than pi 1. We saw that, right? When they are equal, then that is the terminal. That means they are optimal, right? As long as they are not optimal, so pi 2 will be better than pi 1. So that's what policy improvement guarantees us. So you can actually write that down as a policy improvement theorem, which we haven't looked at in the course lectures, but it is covered in the supplementary material that you have if you want to look at it in greater detail. So what we know is that even if I am looking at epsilon greedy policies, right, not just greedy policies, even if I do only epsilon greedy policies, I am still guaranteed to get a better policy than the previous iteration by my policy improvement theorem. Okay, so that's something to keep in mind. So why do we need epsilon greedy policies? So remember, I am actually picking actions according to the Q function to behave, right? So because I am picking actions according to Q function to behave, and we already know greedily picking actions, right? We saw that in the bandit case itself, right? Greedily picking actions can lead to something suboptimal. So we need to have some form of exploration, and the simplest form is to do epsilon greedy. You could do softmax, you could do other kinds of count based exploration like we did with UCB. You could do that also in the context of TD control, and that will also work, right? That's also a well defined algorithm, right? But the simplest one is the epsilon greedy case, and so we'll just look at that for the time being, right? So putting all of this together, we look at our first TD control algorithm called Sarsa, right? Sarsa is called on policy. I'll come to this in a bit. TD control, right? So on policy control, that means that we are able to draw samples from the world, right, according to the policy that we are trying to optimize, right? So we have to remember in this kind of a generalized policy iteration, we have a policy pi that we try to evaluate, and then we try to improve on the policy pi to get the next policy, right? So in on policy algorithms, we are able to sample transitions in the world. Remember, TD actually learns through samples, right? So in on policy algorithms, we are able to sample from the world according to the policy that we want to evaluate. Right? So we have a certain policy that we would like to evaluate. We go and sample from the world according to that policy, right? And then we keep improving the estimate of the value function for the policy that you just estimate, you just sample, and then you do a policy improvement step based on that re-estimated value function, right? So that's basically the idea here behind on policy methods, right? So opposite of on policy will be off policy. So we will see that in the next the next set of slides, right? So going back to look at Sarsa, right? So remember that we have transitions of this form, right? Our trajectory is going to look like ST, AT, RT plus 1, ST plus 1, AT plus 1, and so on and so forth. In this case, I really need to pay attention to what the action I took is, because I'm actually trying to change the policy, right? So earlier, I was just given a policy and I was only looking at, finding the value function corresponding to the policy. So I could just look at the sequence of states and rewards when we looked at the TD0 algorithm, right? So when I'm going to look at Sarsa or Q-learning that we'll see after this, you have to pay attention to the actions also, because I need to know what actions I took so that I can improve on the policy. Right? So I'm going to have this for every transition from a non-terminal state, right? From a terminal state, there is obviously no transition that's going to happen. For every transition from a non-terminal state, I'm going to do this, right? ST. Right. So, what does this look like? This is basically the TD0 update, right? This is TD0 for Q. So, earlier what we would have had? We would have had V of ST is equal to V of ST plus alpha times R plus gamma V of ST plus 1 minus V of ST. That is what we would have had for the value function. This is just the TD0 update for the Q function. So, you look at not just the V of ST, also look at the action that you took at that time, and likewise you do not just look at V of ST plus 1, we also look at the action you will take at time AT plus 1, Q of ST comma AT plus 1. So, this basically allows you to compute the value function using this kind of iterative averaging setting, right. So, we talked about this, how this will converge to the V function when we looked at TD0. Likewise, this update, which is exactly TD0 for the Q function, will converge to the Q function if I allow this to run without changing the policy, right. And notice, always remember that you set the value function for the terminal state to 0, right. So, if ST plus 1 is terminal, then this will be 0. So, that means you will just have RT plus 1 minus Q of ST AT, just like we had in the simple case with that Monte Carlo versus TD, right. So, whenever B terminated, it was just looking at the average reward, right. It was not really looking at anything going into the future. Okay. So, I hope this makes sense. This is the TD0 update. Now, what is the policy improvement stage coming in? The policy improvement stage comes in because we are doing epsilon greedy with respect to the current estimate of the Q function. So, when I go to state ST plus 1, the action that I pick, the AT plus 1 I pick in ST plus 1 is picked epsilon greedily according to the Q function at ST plus 1, right. Therefore, I am in some sense improving upon the existing policy by acting greedily with respect to the current estimate of the value function, and therefore, you have the policy evaluation stage and then the policy improvement stage. Because in generalized policy iteration, each of this basically constitutes one update, right. And I'll look at the algorithm first and then I'll come back to the convergence point, right. So, here is algorithm. So, I initialize QSA like we always do, we initialize it arbitrarily, and then for start from some state S, right, choose A from S using the policy derived from Q, right. Ideally, you would do something like an epsilon greedy policy, right, and repeat for each step of the episode, right. Take action A, observe the reward, observe the next state, right, and now what you do is choose the action from the next state. Now, remember, you have to commit to what action you will take in S prime, right, before you actually perform it, right. You have not performed the action in S prime, you have only performed the action in S, right. You picked an action in S and then you have performed the action, you have observed the next state, right, and the reward. So, basically you start in S, right, you pick an A, then you observe S prime and R, then what you do is you pick A prime, right, but don't perform it yet. You pick A prime and you wait, right. Now, again epsilon greedily. Now, what you do is you come back and do this update, right. So, you do this update, right, and then what you do after you have done this update, you have changed the value of this QSA, right. Now, you set your current S prime to S, you set your current S prime to S, then current action A to A prime, and then you come back in the loop, then you take action A. At that point, you actually take action A, and then you observe the next transition, okay. So, you pick action A prime, use that for updating the Q function SA, then you perform action A prime to go to the next state, right. So, in some sense, so this is your evaluation step, right. So, this function is your evaluation step, right, this update, and this where you are picking actions epsilon greedily, right, is your improvement step, right. So, we do not actually have an explicit policy representation, therefore, we do not write the policy improvement stage explicitly, it is just done implicitly when you pick actions from the Q function, okay. Make sense? Good. And you keep repeating this until S is terminal. So, that is one episode is done, and then what you do, you restart and then keep going with another episode. Keep doing many episodes until your Q function has converged to the level that you want. Okay. So, one way of thinking about Sarsa, remember I was drawing this function, this picture in the generalized policy iteration, right. So, you have your Q pi, you have your greedy function. So, you start with some Q, then go to behave epsilon greedily with respect to that Q, right, and then that will allow you to update your value function estimate. You will go to a different Q function, and then you behave epsilon greedily with respect to that Q function, then go back to another one and keep going back and forth until hopefully eventually you will converge to Q star and subsequently pi star, right. So, because we can formally show that Sarsa is a form of generalized policy iteration, and if it satisfies the following conditions, right. First condition is all state action pairs are visited an infinite number of times. Very hard to satisfy in practice, but that's why one of the reasons why you need the exploration, so that you'll keep moving around. Right, not always, not very quickly concentrate on just the greedy action, right. So, all state action pairs are visited an infinite number of times, right. And the second condition is the policy converges in the limit to the greedy policy. So, what we mean by that? We mean that epsilon goes to 0 eventually. That means that you will have to be greedy with respect to the Q function. So, both of these are satisfied. So, that means your epsilon can't go to 0 very quickly. It has to go slowly to 0, so that you have enough time to visit all state action pairs an infinite number of times. So, and also you would want to, might want to, whenever you reset to a new state for starting a new episode, you might want to do that at a random fashion as opposed to restarting every time in the same start state, unless it's like a game where you have to start from the same location. But otherwise, if you have this option, it will, in practice, it makes it easier if you are able to reset to any arbitrary state and then start generating a trajectory from there, because that allows you to visit all the state action pairs quickly. Right. So, these are the two conditions. So, this is called greedy in the limit with infinite exploration, GLIE. Right. As long as you satisfy this GLIE condition, greedy in the limit with infinite exploration, this will work, this will converge, right. Sarsa will converge to the optimal policy. So, there is one point that I would like to reiterate now, right. So, remember that we choose A prime from S prime, right. We choose A prime to perform from S prime before we do the update, right. So, when we are doing the update, it's possible that S and S prime are the same states. Correct? When you could go from yes, you take an action and come back and end in the same state yes, right? It's possible, right? With all kinds of, so for example, you try to move off the edge of the world and then you hit a wall in the thing and then you stay wherever you are, right? It's possible that you are there, right? So, what might happen, because you are making an update to the Q function in the next stage, right? If I go and pick another action, right, from the same state, it might not be the same action. There are multiple ways it could be different. Because first, I have selected epsilon greedily, right. So, therefore, it is still a probabilistic choice. I might pick a different action, right. But also the fact that the greedy action itself could have changed because I have made this update, right. My value for A could have gone down or the value for A could have gone up now. So, that whatever was the greedy action earlier now is no longer the greedy action. So, if I go back and pick another action, right, I might be sampling from a different distribution, right. So, sometimes that might lead into trouble. That basically means that you are not keeping up your promise. You said that you will make an update according to the current policy, right. You will do the evaluation according to the current policy, but you are not doing it according to the current policy. You are doing it according to a different policy, right. And therefore, that might cause some problems, right. And so, you don't do that. So, you have to remember. So, you are making a commitment that you will choose action A prime from S prime here and you stick with the commitment and you do perform A prime from S prime. More often than not, this will not show up. It's a mathematical thing that it might become a problem. If you make a mistake in the implementation and you actually repick the action, very highly likely it will work, right? It's not something that's going to break your implementation, but it's a good idea not to do that, because mathematically it's a little off.